In this lecture, we're going to talk about powers. We're going to introduce powers and we're going to look at its properties through some simple examples. So first, what is the definition of power? A power is defined as a to the power n. It's defined as, when n is positive integer, it's defined as a times a times a times a, n such a's multiply together. That's the power of a to the power n means. And in this, a is a so-called the base, just a terminology. N is the exponent. And in here, we're going to limit n to be a positive integer, meaning that a equals 1, 2, 3, 4, so on. And you will see later, in later years, that n really can be anything. It can be a fraction, it can be a rational, it can be even irrational numbers. It does not really matter. But in here, we're going to follow the path of how powers were first introduced, and we'll limit our focus on n being a positive integer. In this definition, a to the power n equals really defined as n a's multiplied together. First, we wonder why we want to define power. This is actually very analogous to the definition of multiplication. Remember how we define n times a. This is really a shorthand way of saying that we have a plus a plus a, n such a's adding up together, and we define n times a. And why we want to do that? Because it's just a very convenient way of writing summation of the same number a multiple times. We're using multiplication. Now, a similar situation happens for multiplication. A times a, n such a's multiplied together. If we have to write this, multiple times, it's really inconvenient, right? And you know that mathematicians like to introduce notations to simplify their writing. And this is really a way of simplifying the writing. A to the power n is really defined as a times a times a, n such a's multiplied together. This is the definition. And now we're going to look at a few examples to see how the powers are actually used in calculation. So let's first look at a equals 2. And a power sequence, we can look at what's a to the power 1. So 2 to the power 1. And we know that it's a 2. What's 2 to the power 2? We know it's 2 times 2 equals 4. What's 2 to the power 3? It's 2 times 2 times 2 equals 8. All right, what's 2 to the power 4? It's a times 2, right? 2 times 2 times 2 times 2. And if you observe carefully, 2 times 2 times 2 is just the previous 2 to the power 3. So this can be written as 2 to the power 3 times 2, which is 8 times 2 equals 16. And 2 to the power 5 becomes 16 times 2. Now you see that this so-called has a recursive relationship. This equals 32. So in here, for 2 to the power something, it's basically doubling, the sequence doubling every time. And remember this in the finding number sequences, the patterns in number sequences. This you see the ratio between the current number and the next number is a constant. Indeed, if you take the ratio of the next number over the current number, this sequence is always have a ratio 2. And this has the basically relationship between this lecture and the lecture about finding simple patterns. But another thing is you see this sequence of number grows very fast. Right now, the sequence goes 2, 4, 8, 16, 32. If you calculate 2 to the power 6, this is going to be 64. I'm going to skip a little bit, and I'm going to write down the number. 2 to the 7 is 128. How about 2 to the power 10? This number equals 1024. How about 2 to the power 20? Remember, this is 2 times 2, 22 is multiplied together. This will be equal 10 2's multiplied together times another 10 2's multiplied together. Okay, think a little bit about this. This equals 1024 times 1024. Approximately, this equals 1 million. So you see, the 2 to the power 20, meaning that 22 is multiplied together, it's close to, actually slightly more than 1 million. How about 2 to the power 30? This is going to be approximately 1 billion. How about 2 to the power 40? This is approximately 1 trillion. So you see that I'm only using 2 to the power 40, two kind of very small numbers, but this number is already close to 1 trillion. How about 2 to the power 50? This is going to be 1,000 trillion. Okay? So this sequence of number using powers grows very, very fast. Actually, there's a name for it. It's called exponentially growing. It grows very fast. If you kind of plot using the index of the power, so I'm using the exponent as the x-axis value. So from 1, this is meaning 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 5, 6, 7, 8. And this is the value of 2 to the power k. So here the value is 2 to the power 1. We put here, which the value is 2, right? 2 to the power 2 is going to be somewhere 4. And then 2 to the power 3 will be 8. So this whole thing, if you plot this thing is grows. Okay, I'm not drawing very, very nice. It grows very, very fast. It's not going to be so-called linear, exponential growth. So in here we have this simple property of that. If a equals 2, the sequence a to the power n, which is this power sequence, grows very, very fast. Is it always true that the sequence is going to grow very large and very fast? Not necessarily. Just right now, we talk about when, if you choose a equal 2, the sequence 2 to the n, meaning that the sequence of n equals 1, 2, 1, 2 to the power 2, 2 to the power 3, 2 to the power 10, 2 to the power 20, you know, this sequence grows very, very fast and grows very large, exponentially grow. Is it always true that this thing will go to a very large number? No. Let's actually look at when a equals 1/2. What is 1 over 2 to the power n? This sequence goes. If n equals 1, this is equals 1 over 2, 1/2. When n equals 2, this is 1 over 2 times 1 over 2. And we know it's 1/4. How about n equals 3? 1 over 2 to the power 3. This equals, of course, 1 over 2 times 1 over 2 times 1 over 2 equals 1 over 8. How about 1 over 2 to the power 4th equals 1 over 16. I'm going to skip slightly because this, you can think about this as 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2. 4 1 over 2 multiplied together. And this can be thinking about 3 1 over 2 multiplied first and then multiply 1 over 2. But 3 1 over 2 multiplied together is 1 over 8, as we see from the previous one. So this whole thing, the whole thing is 1 over 16. 1 over 2 to the power 5th is going to be 1 over 32. It's basically half of 1 over 16. In fact, you see that this 1 over 2 to the power 10, for example, this is going to be really equals 1 over 2 to the power 10. Every time you are half of it, it's the same as every time you are doubling the denominator and 1 over that denominator. This equals 1 over around 1 over 1024. So this is around 1 over 1000. Okay, so this all can be said 1/1000th. How about 1 over 2 to the power 20? This is going to be 1 over 1 million, roughly. And then 1 over 2 to the power 30, going to be around 1 over 1 billion. Okay, so here you see this sequence. If you're making the powers, this sequence, if I draw it, the same draw as on the x-axis, it's by putting the power 1, 2, 3, 4, 5, and so on. And here is the value of 1 over 2 to the power n, for n equals 1, 2, 3, and I'm going to plot the value. So for 1, it's going to be at 1/2. For 1/2. At the 2, it's going to be 1/4. So this thing is going to be go down to 0 very, 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 very fast. Okay? And remember, for the other 2 to the power, it actually goes from here, goes up very, very fast. So this thing is going to 0. So it's not necessary that all the power sequence going to be very large. It can go down to 0 very fast. And that all depends on what is the base of A. Actually, when A is bigger than 1, then the sequence AN is going to grow very, very fast, very large. If A less than 1, this sequence A to the n is going to go down to 0. Think a little bit why it's never below 0. It's going to go to very close to 0, but never reach 0. And pretty fast going there. And another thing that you see from this simple example, the 2 simple example is, if you look at 2 to the power 3 times 2 to the power 4, this, if you calculate, this is equals 8 times 16 equals 128. And that's equal to 2 to the power 7. So 2 to the power 3 times 2 to the power 4 equals 2 to the power 7. Okay? Now, if you're using the definition of the powers, 2 to the power 7 really meaning that it's 7 2's multiplied together, and this is 4 2's multiplied together, this is 3 2's multiplied together. So, of course, without calculation, I know 2 to the power 3 times 2 to the power 4 equal to the power 7. Because here, there's 3 2's multiplied together, 4 2's multiplied together, so total is 7 2's multiplied together, which is exactly the definition of 2 to the power 7. In the next lecture, we're going to look at the properties of powers in a much formal way. And this is the end of this lecture.